Hello and welcome. Today's lectures we are going to discuss the topic chemical thermodynamics. In these topics we have see the Gibbs-Helmholtz equation. For this isothermal process we are see delta G is equal to delta H minus T delta S. Equation first. This equation are represent the change of free energy, enthalpy and entropy. But you know that the dz upon dt at P is equal to minus S. This equation second. Hence, two different entropies like S1 and S2 are dz1 upon dt at P is equal to minus S1, dz2 upon dt at P is equal to minus H2. This equation third. By differentiate between these two entropies, we get minus H2 minus S1 is equal to dz2 upon dt at P minus dz1 upon dt at P, equation fourth. Then this S2 minus S1 is delta S equal to D as a common, G2 minus G1 as a delta G, and dt will be common, so dt are here at the P. Therefore, the minus delta S is equal to the delta G upon the T at P, equation 5. Then value of this minus delta S, put this equation 1, we get, therefore delta Z is equal to delta H, this minus and this minus get plus, so plus capital T d into delta G upon dt at P. This equation 6. This equation 6, which is called as the Gibbs-Helmholtz equation. The next point we are going to discuss the thermodynamic open systems. First points are here: partial molar properties. We know that in thermodynamic functions like internal energy, free energy and enthalpy, they are extensive properties of the systems, means which depends on two other parameters like temperature and pressure. Upper depends on the amount, and hence the thermodynamic functions becomes a functions of several variables. If capital X be the extensive property of the system, then it will be depend on the temperature, pressure and number of moles of different components. The make the system as capital X is equal to the functions of N1, N2, N3 at dash dash at a constant temperature and pressure, where this N1, N2, N3 are the number of moles of the component, the 1, 2, 3 having the temperature and pressure to indicate this capital T and capital P are the pressure and temperature of the system. A small change in magnitude of this property will be due to change in the temperature and the pressure of the system and moles of different components. Then we have seen mathematically if this small z is a function of two variables like x and y, then small change in z will be dz is equal to dou z by dou x at y dx plus dou z upon dou y at dy. Then we have see the finite change of this dx of intensive property or thermodynamic functions, which is given by dx is equal to dou x by dou t at p(n1 n2) dt plus dou x by dou p at t(n1 n2) dp plus dou x dn1 dou n1 t pn2 dn1 plus dou x by dou n2 at t1 p1 n1 n3 dou n2. The quantities like the dou x by dou n1 and dou x by dou n2 in above equation, they are referred as the partial molar quantities. Similarly, the other partial molar properties like which is represented by using bar over symbol for the properties. Therefore, x1 bar is equal to dou x by dou n1 at t1 p1 n2 n3. x2 bar is equal to dou x by dou n2 at t1 p1 n2 n3, and similarly the other partial molar properties like the V bar, like a partial molar volume, V bar is equal to dou V by dou n1 at Tp n2 n3, and the free energy like a G bar is equal to dou Z by dou n1 at T pn2 n3, and therefore hence the partial molar property of component is defined as the change in magnitude of that property due to addition of 1 mole of that components. In such systems, a large quantity of the system, that addition of moles does not lead to any change in temperature, pressure and composition of the systems. It can be approximately change in magnitude of the extensive property of the systems per mole of the components. The next points we are going to discuss the partial molar volume. For partial molar volume of the ith components is defined like V I bar is equal to dou V upon dou Ni at T P Nj, where this Nj means the number of moles each components, number of moles of each components is held constant except the ith component, except the ith component. The partial molar volume can be defined as the change in volume like capital V when 1 mole of ith component is added to a large quantity of the system at a constant temperature and pressure, which is called as the partial molar volume. Partial molar volume means if the large volume like capital V, they will be changed, which times like a 1 mole of ith component, they will be added to the large quantity of the volume of the system at a constant temperature and pressure. This is called as a partial molar quantities. Consider we have taken like a binary mixture having a two different solutions. Then dV is equal to dou V by dou T at Pn1 n2 dt plus dou V by dou P at Tn1 n2 dV plus dou V by dou n1 at Tpn2 dn1 plus dou V by dou n2 at Tpn1 dn2, but at a constant temperature and pressure. Then this equation are like dou V at constant temperature and pressure is equal to V bar 1 dn1 plus V2 bar dn2. Integrating of this equation, then we get V is equal to V1 bar n1 plus V2 bar n2. Thus, the volume capital V of the solution may be calculated for a given concentration using above equation if the partial molar volume like a V1 bar and V2 bar at a given concentrations are known. So total volume of that solution, they will be calculated by using those equations. How will you calculate? By knowing the values of the partial volumes like a V1 bar and V2 bar at a constant temperature and pressure. The next points we have see is here the chemical potential like the partial molar free energy. Partial molar free energy can be defined as the Gi bar is equal to dou Z upon dou Ni at a constant temperature, pressure Nj. The partial molar free energy are also known as the chemical potential, and which is represented by using the symbol as mu, and therefore this mu I is equal to dou Z by dou Ni at a constant temperature, pressure Nj is equal to Gi bar. This Nj indicate the number of moles of each component is held constant except for the ith component. So the chemical potential of any component can be defined as the change in free energy of the system if 1 mole of the component I is added to a large quantity of the system at a constant temperature and pressure, which is called as the partial molar properties. But chemical potential is the derivative of extensive property, and therefore it is an intensive property like temperature and pressure. The chemical potential is independent of the size of the system. The name chemical potential, they will be signifies like electric potential, gravitational potential, and it is driving force, and therefore it is the chemical potential that determines whether a substance will undergo chemical reactions or not, and hence this potential of any components can be defined as change in free energy of the system if 1 mole of component like I is added to a large quantity of the system at a constant temperature and pressure. For binary mixtures of the solutions, then solution can becomes this equation like dz is equal to dou z by dou t at Pn1 N2 dt plus dou z by dou p at Tn1 N2 dp plus dou z by dou n1 at Tpn2 dou n1 Tn1 plus dou z by dou n2 at Tpn1 dn2. At a constant temperature and pressure, for those equation we can rewrite like at dg at a constant temperature and pressure is equal to g bar 1 dn1 plus g bar 2 dn2. Similarly, other equations like chemical potentials dz at a constant temperature and pressure is equal to mu1 dn1 plus mu2 dn2. On integrate both equation, then we get this equation firstly. So on integration of this equation, therefore g is equal to at a constant temperature and pressure is equal to g1 bar n1 plus g2 bar n2. Similarly, those equation like z is equal to at a constant temperature and pressure mu1 n1 plus mu2 n2, mu1 n1 plus mu2 n2. But you know that in general for this free energy, like a capital G at constant temperature and pressure is equal to summation mu I into Ni. For single components, then we have used capital Z at a constant temperature and pressure is equal to the N mu is equal to N into Z bar, and therefore the mu is equal to G bar is equal to capital G upon N, and therefore for a pure substance the chemical potential is equal to its free energy per mole variation of chemical potential with the pressure and temperatures. So such types of the chemical potential and free energy for a pure substance is equal to their free energy and chemical potential per mole variation of chemical potential with pressure and temperature we can calculate. Thank you.